Alright, so hopefully everybody's doing well. Today's going to be more of a worksheet. I really want to kind of go over the right-hand rule. So there's actually a couple of right-hand rules. This is the first one. So if you do Google it, you might actually see other kind of right-hand rules where they have like three different fingers. The thumb is going to be like a field. I think the current is this one, and then this would be like the force. We'll get to it later. But today we're going to do the more simple one, which is your thumb is going to be the current, and then your fingers are going to be magnetic field. So I have a couple examples that I want to kind of go over. We'll do our best through this. Like I said, it's not perfect. It's already hard enough to do in person, but it is something that I think it's worth trying to do online. And like I said, do your best. I expect everybody to do well during this time. If you haven't heard, our quarter got extended, so we'll see how that goes, and I'll update you grading wise. But I'll be honest, I'm going to be fairly generous, if not very generous, with our grades this quarter and probably fourth quarter. So don't worry about grades. We're good. I just want to try to get as much content in so that if you do take physics in college, that at least you kind of have this in your background already. So what I have in front of us is kind of a classic kind of schematic of an electrical circuit. So we haven't completely done electricity yet, but let's just say this is a loop. And right here, usually the bigger line represents positive, and the smaller line represents negative. So if this was a battery, this is the negative end of the battery, and this is the positive end of the battery. And then we have a wire that connects the two. So if it's connected, what that means is that electrons are going to move around this thing. Now, we know now that electrons move from negative to positive. So the negative charge wants to get to the positive charge. When you connect it, you create a circuit, and you get a flow of electrons that goes through here. Now, the weird thing is that Franklin was pretty much the person that created, or not created, but termed current. And the way that he termed current was the complete opposite. For him, he said that current moved from the positive to the negative. So we're going to stick with that. So this is current. And current moves from positive to negative. Usually you might see it as I for current, and it's going to move in that certain direction. So even though we know electrons move from negative to positive, current traditionally is positive to negative. So if you have a traditional book, traditional worksheet, that's kind of how they're going to do it. Now what we want to do is figure out, okay, we know when electrons are going through any kind of motion, even if you shoot an electron straight, it does carry a magnetic field. When you have a current here, it's going to have a really predominant magnetic field, and it follows the way of the right-hand rule. So remember, in the right-hand rule, let me get my colors. And I apologize for my ugly hand drawing, but that's your thumb, and here's your fingers. So remember, the thumb represents the current, and then your fingers represent the magnetic field. So like I said before, your hand can only curve in one direction. So if I have a piece of pen here, I can't grab it this way. I can only grab it this way. I mean, I could have my left hand, they do superimpose each other, but they do curve the opposite direction. So my right hand curves this way, while my left hand curves this way. And I think the video is mirrored, so I apologize. But anyway, right hand rule. This is my right hand. So if I have this and I grab, my fingers loop around this pen in a certain way. So you'll notice that if the current is in the direction of my tip, my fingers loop around and does a circular path around here. So what we want to do is kind of figure out, okay, if this is the what's it called, the current that's going around, what does the magnetic field look like around here? So let's do the first one, the one on the right. Let me label it. Let's say this is the first side. So here, the current is going up. So that means I'm going to grab my right hand. I am going to grab my pen with my thumb pointing in the same direction as the current, and then I'm going to have my fingers wrap around it. Now, as I'm looking at it on my screen, my finger is going in the counterclockwise direction around this wire. And I know this is extremely difficult online, but it's going to come this way, over this wire, and like this. And notice that my wire goes over here, but it doesn't cross the wire here. So that means if this is the wire, if my finger is wrapping around it, you don't see my finger the pen is in front of the finger, so that part doesn't seem, but when it's in front, my finger covers the pen. So you'll notice that here, let's say this was the thicker arrow, and I colored it in. The front side is covered, but the back side is not, so it goes around. Let's do the same thing now going to the second part. And this time it's going to the left. Oh gosh, it's going to be hard. But anyway, trying to imagine how you guys will see it. Hopefully this is in the right way. Hopefully. So if I grab it like this, my fingers to the left. In the front, it's covering the pen. In the back, it's not. So it's just looping around in the circle. So in the front, going to go like this. It's not going to cross the bottom, and it's going to do that. Okay. Downwards here. If I have it ground like this, notice that in the front, my fingers are in front. In the back, it's not. So if I grab it like this, it's going to go like this. Let me make sure I got that right. Yes, I did. The bottom, it's going now the other way. Hopefully I'm getting it right. I'm sorry, it's mirrored image. And you're going to grab it like that. So let me make sure I get it. So it's going to be covered in the back, not in the front. So it's going to look like this. Okay, so like I said, this is extremely difficult when we're in person, but even more difficult when we're not, but hopefully that kind of makes sense. Now, these loops does make it a little bit more difficult, and I'll probably also do like a Bozeman Science as well, just because he has a little bit better computer graphics than me. But if we kind of rotated this loop, let's say the loop right here is flat, but let's say we rotated it a little bit tilted. So now, let's see if I got this right. If I rotate it this way, this will be the first end, this will be the second end, this will be the third end, and hopefully you kind of see how I just rotated around in that. So if we did that and the current is still the same, the current's still going positive to negative. Okay. We could do the same thing, and hopefully this way it'll make more sense. So if it's a top cross-sectional view, the magnetic field will look like this. On top will look around like this, and then on bottom will look like this. So hopefully you'll be able to, let me make sure I got that right. I think I got the bottom one wrong. I got the bottom one wrong. It looks like that. Let me make sure I got the top right one. Yeah, that one's right. So you'll get that. So when you notice this, and like I said, this is difficult to do in person, you'll notice that here the arrow is always coming out from inside the loop. Okay, no matter where you are in the loop, the side, the top, or the bottom, it's always coming out. So another way of drawing this, so instead of drawing this, we could do kind of a flat instead of a non-3D thing. So when you do this, this is the tip of the arrow, and then if you have X, that's the butt of the arrow. So if we kind of flatten it right here, the tip of the arrow is coming out. Right here, the butt of the arrow is going in. Tip of the arrow is coming out. Butt of the arrow is coming in. Tip of the arrow, butt of the arrow, tip of the arrow, butt of the arrow. So you'll notice that it's always going to have the same pattern on the inside compared to the outside. I know this is, like I said, it's going to be difficult. We'll do it for like a couple practices. And I'm going to try to post up some videos of other people doing it as well, so hopefully it makes sense. This worksheet does have other things involved, but what I like you to do is just to mentally try what I have here. So let me kind of just save this. So if I scroll down, let me get rid of the drawings. So skip this. This is the same thing, but the opposite direction. Notice that the positive is on the left side versus here where the positive is on the right side. So just mentally figure out which way it's going. That's pretty much what I want you to try with today. It's the right-hand rule. I'll try to also post up other videos with it as well. And the goal is just to understand like which way it goes when it comes to a straight wire line, and then the more important one is a loop, because if you notice all electromagnets have loops in it, and it's because of this property where when it's in the loop, the inside of the loop, the magnetic field is always pointing the same way, no matter if it's top, side, or bottom. On the outside, it's always pointing a certain way, no matter if it's top, bottom, or or sideways. And because of that, it's going to look just like a bar magnet, which we'll get into. So hopefully that makes sense. I do kind of have a couple of things I'd like you to just watch and practice, and then maybe we'll do a little bit more, and I'll probably have like a multiple choice kind of thing where you could click on what's happening to the arrow at certain points kind of as practice. Like I said, this is a difficult thing in person. I can't imagine how difficult it is to try to understand it on a screen without three-dimensional like references and stuff. So remember, we're only here to learn extra stuff. Grades are generous. Don't freak out. Yes, we're gone until May 5th, and we'll see how that goes. But the good thing is, I think it's official. It is official. Standardized testings are all canceled, so you're not going to do SBACs when we get back, and APs are different. So we'll hang in there, and we'll all do it together. All right, take care.